hot, dense state that nearly 14 billion years ago expansion started. Wait, the earth began to cool, the autotrophs began to drool, Neanderthals developed tools, we built a wall. We built the pyramids, math, science, history, unraveling the mystery that all started with a big bang.
I'm just saying that, if time and space are not absolute, shouldn't some people age faster in comparison with another?
Well, you look like you're in your early 60s.
Excuse me?
No?
Back to my point. There's no possible way that the guy you're watching live on your iPad is performing simultaneously back in Pakistan?
No, it's India. India.
Right. There's gotta be some sort of delay in which the image travels.
So back to this again. Time is relative to something. Well, we all know that you're an Einstein fan, but hypothetically, that shouldn't affect your judgment.
We have a combined IQ level of 360. Do you think I'm that shallow?
No, you're wrong. 200 is from me. No,
Hello, peasants of science community. I'm Sheldon Cooper, BSc, MSc, PhD, SCD, OMG, right? So I heard about your childish discussions about special relativity. Let me enlighten you on what is special relativity.
no.
At the turn of the 20th century, most of the physics community enjoyed a sense of accomplishment. Newtonian mechanics, based on Newton's law of motion, provided the principles by which all matter behaved. Building on James Clerk Maxwell's mathematical description of electric and magnetic fields, physicists successfully unified the subjects of electricity, magnetism, and optics. Maxwell's ideas had an apparent answer to the true nature of light. Light is a combination of oscillating electric and magnetic fields, hence electromagnetic waves. At that time, only a few questions remained. The nature of an atom was still unclear. Contrary to Maxwell's assumption that electromagnetic waves, like all waves, needed a medium, there was totally no evidence to support this. Physicists expect to solve all these problems within a framework of familiar physical models and principles. However, new models and principles are needed to be developed in order to explain all these problems, and these new ideas radically changed the way physicists understood their once familiar universe. One of the main contributors to these new models was Albert Einstein. Einstein was thinking, if the current methods cannot solve all these problems, what is stopping us from analyzing the problem from a new approach? With a fresh approach in mind, he started analyzing these problems using a new technique, thought experiments. What is thought experiments?
Thought experiments is a method exercise used to investigate the consequence of a hypothesis or postulate. Simply said, it's doing the experiments in your brain.
Does anybody in this room know what is special relativity? Okay, I think I underestimated your mental capability. Okay, let's start with the first question in every physics class. What is a frame of reference?
Why don't you let me explain? I'm a physicist, you know.
So, what is frame of reference? Simply say, a frame of reference is a region where observations are made. In the same frame of reference, the observation made should be the same regardless of the observer. Therefore, when conducting an experiment, everyone will get the same reading when their frame of reference are the same. Now, let's see what happens when you have two different frames of reference and how are they different from each other. So, this is a stationary observer called Enoch. Enoch is observing Quicksilver and Flash running away from him because he is about to fart. Now, ask yourself, what does Enoch observe? Enoch sees Quicksilver and Flash running away as fast as possible from him. Okay, Enoch finished farting, and now let's change the observer to Flash. What does Flash observe? Flash is actually seeing Quicksilver face to face, as Quicksilver is stationary relative to Flash. How about Enoch? Flash actually sees Enoch moving backward from him. For extra information, Enoch is also acting as a reference point. A reference point is a fixed point in a frame of reference where it is used to measure the speed or distance of Quicksilver and Flash relative to Enoch.
How? Do you know anything about relativity?
That's so simple. Relativity simply means that all objects move relative to each other. We will only know that we are moving if we have another object or frame of reference. Without them, we will not know whether we are moving or not. This is because in all inertial frame of references, the laws of motion are still the same. Without a guide or indicator, we will never know whether we are moving or stationary since the laws of motion are the same in all inertial frame of references. We can determine whether the frame of reference that we are in is accelerating or not because of the nudge due to inertia when the frame of reference accelerates or decelerates. Let's put a tree in space. Without any objects around it, there's no possible way for the tree to determine whether it is moving at a constant speed or whether it is stationary. So let's introduce a dog near the tree. From the tree's point of view, the dog is actually moving forward. However, there is still no possible way to confirm whether the dog was moving forward or the tree was the one moving backward. So what we can say is that the dog was actually moving forward relative to the tree, or the tree was moving backwards relative to the dog. So which one of it is true? Both of it are true, as there is no possible way of determining which one is actually moving and which one is not.
Does anybody know about special relativity here after we have discussed relativity and frame reference?
See, special relativity is
That's such an easy question. Let me answer this. I'm a physicist.
by that logic, I should answer all anthropology questions because I'm a mammal. Now, where were we? Special relativity. Special relativity is.
To answer special relativity, we should start with Einstein's postulates. Postulate means a statement assumed to be true from which a theory is developed. Einstein has two postulates. The first postulate is the laws of physics are the same in all inertial frames of reference. There is no physics experiment can ever determine whether you are at rest or moving at a constant velocity. Say, we put Flash in a windowless box. So, Flash wants to know whether he is in a stationary box or a moving box. But from his point of view, he is oblivious about the outside world except his own. He does not know whether the box is moving with a constant speed or in stationary because he cannot see what is happening outside. It is because when you want to know whether something is moving, you need to compare and relate it to another object. The box may be moving at the speed of light constantly and he does not know that. Therefore, without the help of other frame of references, except his own, he does not know whether the box that he is in is moving or not. Now, take a look on another example. Suppose you are on an airplane flying smoothly in a constant speed. Enoch across the aisle says, "Hey, toss me your bag of peanuts, will you?" Since you know Enoch is a charmer and you want his attention, you immediately grab the peanuts. But you stop to think that something is not right. You ask yourself, I'm on an airplane that's moving at hundreds of miles per hour. Which way and how hard should I throw this bag of peanuts so that it will actually reach Enoch? Well, no, you don't think this at all. You just toss the bag using the exact same throwing motion as you would if you were on the ground. And the peanuts will throw perfectly normal as if the plane were on the ground. You see, if the plane is moving at a constant speed, it in a straight line, then the laws governing thrown objects are exactly the same as in a plane at rest. We call the inside of the plane an inertial frame of reference. The word inertial refers ultimately to Newton's first law of motion. Inertia is the property every object has which causes it to either sit still or move in a straight line at a constant speed, unless there is a force acting on it. An inertial frame of reference is a frame of reference in this condition. So here's the bottom line. An inertial frame of reference is one which is either at rest or moving in a straight line at a constant speed. Einstein's first postulate is that all the laws of physics hold in such a frame. The examples of a moving airplane were just to demonstrate to you that this is a perfectly reasonable assumption that people make all the time without thinking.
So let's say that we're going to shoot a light ray inside a stationary transparent box. From a stationary observer's point of view, the light ray will move at the speed of light. Now, let's say that we are going to shoot another light ray, but instead we're going to shoot it inside a moving transparent box. What will be observed by the stationary observer? Will the speed of light change? So logically, one would assume that in this scenario, the speed of light will be an addition of the original speed of light plus the speed at which the box is moving. However, this is actually wrong. The speed of light is actually the universal speed limit. So, in this case, we'll still be traveling at the speed of light. So Einstein's second postulate. There is at least one inertial frame of reference in which, for an observer at rest in this frame of reference, the speed of light in a vacuum is independent of the motion of the source of light. Simply said, the speed of light is the universal speed limit because the speed of light is independent of the frame of reference. Whether the light is traveling in a stationary frame of reference or a moving one, the speed of light does not change.
So guys, is this related to our initial conversation about time being absolute?
Of course. Let me explain why. People always say that time is absolute. In proposals, people always promise that they will love each other till the end of time. However, according to special relativity, time is not absolute. Time is relativistic. So how is that actually possible?
Imagine me being stuck in a windowless room. Yes, really, windowless room. Sunlight is gone! Sunlight is gone! My son! Where's my son? Therefore, I'm stuck in this room, not knowing whether I'm inside a stationary frame of reference or a moving frame of reference. The frame of reference, in this case the room, can be moving at the speed of light, as long as it is moving at a constant speed. Therefore, I will not be able to know whether it is moving or stationary. Spooky, eh? The time measured inside here is called proper time because the person, is at rest relative to the clock.
However, somebody outside the room will know whether the room is moving or not. When I make measurements of an event happening in my room, the time measured will be different because now we have to take into consideration the speed of the frame of reference. If the frame of reference is not moving, then we can chill because the time measured will not differ. Things start to change when the frame of reference moves. We have to factor in the effect of the speed of the frame of reference on the time measured. The faster the frame of reference moves, the slower the time measured from the guy looking from the outside. Hence the saying, moving clocks move slower. See the difference now? The clock is moving relative to the person looking outside, but the clock is stationary relative to me in this room. Therefore, the time measured by the guy outside and by me are different. Time is not absolute. It depends on which frame of reference are you talking about. So remember, time is not absolute.
What about length?
Yeah, what about it?
Does it suffer the same fate as time?
Yes, let me explain this.
One of the peculiar aspects of Einstein's theory of special relativity is that the length of objects moving at relativistic speeds undergoes a contraction along the dimension of motion. An observer at rest relative to the moving object would observe the moving object to be shorter in length. That is to say, that an object at rest might be measured to be 60 meters long. Yet the same object, when moving at relativistic speeds, relative to the observer, would have a measured length which is less than 60 meters long. This phenomenon is not due to actual errors in measurement or faulty observations. The object is actually contracted in length as seen from the stationary reference frame. The amount of contraction of the object is dependent upon the object's speed relative to the observer. The animation depicts this phenomena of length contraction. In each animation, a spaceship is moving past Earth at a high speed. The spaceship would be measured to be 60 meters long when at rest relative to the observer. Note that the length contraction is only significant when the object is moving at relativistic speeds, speeds which are a significant fraction of the speed of light. Furthermore, note that the contraction only occurs in the dimension of the object's motion. If the object is moving horizontally, then it is the horizontal dimension which is contracted. There will be no contraction of the height of the object. This information is summarized in the table.
I need some biological catalyst, guys, to continue my research.
He just means he is hungry. Shall we get some lunch?
Yeah, we should.
Yeah, let's go. So, do you believe in twin paradox?
Yes, of course. The twin paradox is a very interesting stuff. It's like you have a twin that one of them is being sent in a spaceship running at the speed of light. And when that twin comes back, he'll be younger than the other twin who stays on Earth. How can these two twins with the same age different when that twin comes back from spaceship? Interesting, eh?
Yeah.
So you're saying that, let's say if Raj and I are identical twins, and I was launched to space for, let's say, a year on my watch. So somehow,
Raj look older?
Yeah, Raj would have probably finished high school, let's say 4 years.
What? It took you 4 years to finish high school? Duh.
You son of the biscuit!
Yeah, but you get my drift.
It's okay. It's okay. I finished it in 3 years.
Yeah,
You know, Raj,
What up?
Marvel is mental, man. I mean, why would they even create Quicksilver?
Why not?
Obviously, Flash is still going to be faster.
No, how could you say that? Quicksilver is faster than the speed of light.
Well, Flash runs double the speed of light.
Idiots! Have you gone through college? Come on. Nothing can travel faster than the speed of light, okay? It's the universal speed limit.
They have a combined IQ level of 360.
Let me explain why the IQ is lower than 360.
So why is the speed of light the universal speed limit?
Just remember the formulas for time dilation, length contraction, and relativistic momentum. What do all these formulas have in common? The answer is the expression square root of 1 minus v squared over c squared. Why does this expression prove that the speed of light is the universal speed limit? Let me tell you why. If we put c squared in replacement of v squared in the equation, we will get square root 0 as the answer. Square root 0 produces 0, which makes sense, right? However, if we put values that are bigger than the speed of light, for example, 2 times the speed of light into the equation, we will get a negative number in the square root column. A negative number cannot be square rooted, it only produces an imaginary number. This proves that the speed of light is the universal speed limit.
So, is momentum affected also?
Well, yeah. I mean, Newtonian formulas are only valid when the objects are moving at normal speeds. However, when the object approaches the speed of light, this formula can no longer be used. Instead, we have to factor in special relativity to find out the momentum of the object as it approaches speed of light. So basically, when an object approaches speed of light, its relativistic energy increases, and this affects the apparent mass of the object, which is also called the relativistic mass of the object. The relativistic mass of the object is different in comparison with the rest mass. The relativistic mass of the object would increase as the object approaches speed of light. So basically, the increase in relativistic energy of the object as well affects the momentum, and this can be expressed in the energy-momentum relationship, which includes the momentum of the photon and kinetic energy. And by this, we can determine the relativistic momentum of the object as it approaches the speed of light.
Is knowing all this necessary, guys?
No, you're pretty shallow for someone with 2 PhDs.
Well, I am one in a billion. My existence influences the universe.
These are all fascinating stuff.
Guys, there are many Indians suffering from hunger, but there's one starving here. It's me.
Oh, let's go, dinner.
Let's go! Where are we going for dinner?
Cheeseburger factory, of course.
Yeah, let's go.
Where is it?
I don't know.
Let's turn on our GPS.
Alright.
Do you know what a GPS is actually?
Don't know. What is it?
Do you know it's even related to relativity?
Really?
CSC?
So basically, so how is GPS related to relativity? First of all, you need to know how GPS works. There are 24 satellites orbiting the Earth, and there are 3 extras in case anything fails. And GPS operates on a simple mathematical principle called trilateration. So, trilateration falls into 2 categories: 2D trilateration and 3D trilateration. In order to make a simple mathematical calculation, the GPS server must know 2 things. First, it must know the location of the place to be traced by at least 3 satellites above the place. Secondly, it must know the distance between the place and each of those space vehicles. Units that have multiple receivers pick up signals from several GPS satellites at the same time. These radio waves are electromagnetic energy that travels at the speed of light. Calculation on the distance of the location relative to the satellites and the distance of satellites relative to each other enables the determination of the location of the tracked object. Interceptions between equations of the satellite provide us with the location.
GPS has helped a lot in my life. With the introduction of GPS-based applications such as Google Maps and Waze, I can get my directions to any new place without having to refer to a map. Instead, GPS can track my location and give me directions to that new place that I want to go. I won't even get lost in a total foreign country. I do not need to worry at all because I have GPS-based apps such as Google Maps and Waze.
Industries have benefited from the introduction of GPS. For example, the taxi industry in Malaysia has benefited with the introduction of GPS-based apps such as My Taxi. With My Taxi, a customer can hire a taxi nearby to get to his location. This benefits both sides because, number one, the customer can hire a nearby taxi driver so that he does not need to wait so long for a taxi. Number two, for the taxi driver, he can reach nearby customers with ease. He can save on fuel and he save his time. Governments can use satellites to locate their army, finding missing planes, or even monitor their citizens, like Chicago City in the recent game Watch Dogs. In real life, there's even allegations that the United States are monitoring the whole world through the NSA, even though they are just rumors. But with the advancement in technology and GPS, anything is possible in the future. So beware. So how does Einstein change humanity with his special relativity? Well, first of all, he changed on how people look at space and time. Space and time are not absolute. They change according to the frame of references. The time we measure here and the time we measure from another frame of reference can be totally different. This is totally different from what people understand in the past, where they think that time and length are absolute. However, Einstein proved that time and length are totally relativistic. Sounds cool, eh? Well, Einstein took the risk by thinking time and space from a new approach rather than looking at it from a traditional way. So we can reflect this into our lives and think that, should we take risks when we have the chance? In my opinion, definitely, because risks are actually opportunities for us to be successful. Risks are opportunities for us to face challenges with a new approach rather than trying to drill through a brick wall if we are going to use the old approach. Humans like patterns. They like to repeat stuff that is tried and tested because it is less risky to try something that is already proven successful many times. However, life can be boring when you repeat a pattern over and over again. Therefore, take risks as an opportunity to change your life. It may lead you to different paths. However, the journey will be fruitful and you'll definitely enjoy the view along the way.